In this video we're going to look at some integration of a composed function. The formal way is to use a technique called change of variable or by substitution. Here we're going to use an informal way. So here we have a function y equals sine of x squared minus 4x plus 5. We see it's a composed function. That means when we begin with the value x, we have to first calculate x squared minus 4x plus 5, and then we take sine of the answer. So as a Venn diagram, suppose we take the value x, when we calculate x squared minus 4x plus 5, we get 10, and to find the value y we have to take sine of 10. We usually call the intermediate answer u, just to give it a name, so we'll say y is equal to sine u. Using the notation we learned in first year, f of g of x will be the function x squared minus 4x plus 5, f of x is sine x, then the function f of g of x, so f applied to g, in other words f applied to x squared minus 4x plus 5. F says to take the sine of whatever's in the bracket, so we take sine x squared minus 4x plus 5. So let's do a quick review of taking the derivative of a composed function. Suppose we consider y equals sine x squared minus 4x plus 5. Then we generally set y as a function of u, in this case y equals sine u, where u is x squared minus 4x plus 5. dy by du is cos u, du by dx is 2x minus 4. So for dy by dx, the chain rule says take the product. We take the product, we get cos u multiplied by 2x minus 4. We write 2x minus 4 first, and then write cosine of u. U is x squared minus 4x plus 5. And there is our derivative. So it follows that if I take the antiderivative of a derivative, we're back to where we started. That's a little diagram. Suppose I begin with f of x and I differentiate f of x. I get f prime x. Then if I antidifferentiate that, I'm back to f of x. Oh, plus c. So let's antidifferentiate this derivative that we have on the left hand screen, the derivative 2x minus 4 cosine x squared minus 4x plus 5. We know that's the derivative of sine of all that because we just differentiated. And so we have our antiderivative. Now in blue what we're doing here is we're taking finding the antiderivative of a function very close to the one we just antidifferentiated. We see it differs only by a factor of 2. And so we don't have to have a direct antiderivative. We can sometimes cook it a little bit. So let's suppose then that I just had the integral and I needed to arrive at the antiderivative without first knowing the pair, the differentiating. So here we have 5 steps. 6 steps. So the 6 steps that we have first is we need to identify the product of two functions. We need to look for, in the integrand we need to look for a simple function and a composed function. Then we need to look for an inside function, as in the first step, the first thing you calculate, the thing that you would call u, and an outside function, the thing that you do next, the thing that takes you to the value y. The fourth step is to ask whether the simple function is actually the derivative of the inside function, the first step of the composed function. If it's yes, then all we need to do is antidifferentiate the outside of the composed function and add c. Let's do a few examples to make all that make sense. So in our first example, first we're going to identify a product. There are two functions multiplied together. 3x squared e to the power of x cubed. We identify 3x squared as being a simple function, e to the power of x cubed being the composed function. So it has a first step which is to take x and cube it, and as a second step is to say let's take e of the answer. So in this case our u is x cubed. Now when we take the derivative of x cubed we get 3x squared, which is part of the product. That's good news. Let's see how that's good news. That means we are on to step 5, which means just antidifferentiate the outside. of the composed function. The outside was simply e, and e anti-differentiates to e. So let's check that out using the chain rule. du by dx. So dy by dx is the product of those two, and that is what we began with. Okay, so one way we can think of that is by dividing by the 3x squared. To do that, we can square it out. Let's take another example. Okay, we want to identify, is there a product of two functions of x? Yes. Is one of them a composed function, as in a two-step function? Sine of x all to the power of 6 is composed. First we take sine, and later we raise that to the power of 6. So the outside step, second step calculation, is to raise to the power of 6, a polynomial step. So the derivative of the inside is cos x, which is good news because that's the simple function. So we'll divide by cos x, leaving us with only one part of the chain rule, or we can simply score it out and anti-differentiate the outside part of the composed function. Let's take another example. Okay, so in this case we have the composed function is something or other to the power of 4, and when we take the derivative of the something or other, we get e to the power of x plus 3x, which is the simple function on the left, and that's supposed to be negative. So the outside part of this composed function is to raise it to the power of 4, and so to anti-differentiate the outside part would be raise it to the power of 5 and divide by 5. Let's do that. Divide by 5 plus c. Why do we score it out? Well, remember that when you use the chain rule, for example on a simple function such as cos 2x, that anti-differentiates to sine 2x divided by 2. The chain rule says to differentiate something. Suppose I have y equal half sine 2x. I would set y equal half sine u, where u is 2x. And the last part is to figure out du by dx. And so for the derivative, we'll multiply it by 2. Therefore, for the antiderivative, the first part is we're going to divide by 2. Or divide by du by dx. So when we score out the first part of the function, we're dividing by the derivative du by dx. And the formal notation makes this look official. But here we're just trying to find out what is the thing that differentiates to the integrand. Okay, let's look at another example. Here the product isn't so obvious, so we rewrite it as 1 over x multiplied by ln x all squared. And so our simple function, our composed function is ln x all to the power 2. There's two steps. First we take ln and then we square our answer. And the derivative of the inside function is in fact the other function in the integrand. So to anti-differentiate the outside part, it's raised to the power 3 and divide by 3. Zipping straight on to another example. Again, it's not obvious we have a product, but if we write it as 1 divide cos x multiplied by sin x, we see a product of two functions. In this case, the composed part is 1 divided by 2 cos x. The inside part is to take the cosine. The first thing we do with x is to take cosine. After we've done that, we say 1 divided by cos x. So let's let u equal cos x. So we're saying that the outside function is 1 divided by u. To anti-differentiate 1 divided by u, or 1 divided by something, the antiderivative of that is ln absolute value of whatever's underneath. So since we see that the derivative of sine x is cos x, the derivative of cos x is minus sine x, we can score that out. We need to multiply by a negative to cater for that negative, so our answer is going to work out. And I need to anti-differentiate 1 over cos x, which is ln absolute value cos x, and the negative is there. Last example is very similar. In order to make the second part look like a composed function, we've raised it to the power of 1, and the result is to find the function that differentiates to the thing in the integral. So let's see how this works out. The derivative of ln x is 1 over x, which is good, that's the other part of the product. And let's anti-differentiate the outside of the ln x function, which is raised to the power of 1, or raise it to the power of 2 and divide by 2, and plus c. Now to differentiate that, we find that we have ln x over x.